Welcome to Study Loop.
Hello everyone, today we're doing chapter 18, problem 24, and this problem asks us to draw the products of each of these reactions. So let's see what we have. Well, we have a benzene ring with 3 electron withdrawing groups, and then we have some sort of nucleophile. Remember, sodium is just going to be our spectator ion, and then we have this methoxy that's going to dissociate with a full negative charge on the oxygen atom, acting as a strong nucleophile. So what we have here is nucleophilic aromatic substitution reactions. And this is opposite from your electrophilic aromatic substitution reactions we were doing thus far, in which now instead of the pi bond of the benzene ring being the nucleophile, now we actually have a full nucleophile as the reagent, and now the benzene ring is the electrophile. And this makes sense because this benzene ring has 3 electron withdrawing substituents, which are both inductively and through resonance taking away electron density outside of the benzene ring. So now this benzene ring is very electron poor. We have a good leaving group, one of the halides, chlorine, and we have a strong nucleophile. So right away we can say that a nucleophile will attack this carbon, and then we'll have the breaking of resonance of the pi bond breaking, and then we would lose aromaticity in the form of a carbanion being formed here. And then once that carbanion is formed here, we can push those electrons to form a new pi bond here, push that pi bond there, push this one over here, and because now we would have a carbon with 5 bonds, that's not possible, so our leaving group chlorine would be kicked off to form our final product. That looks something like this. And not only that, we know that your leaving group should be para to your electron withdrawing group because, or even ortho to your electron withdrawing group, because, for example, when we made that initial bond with the nucleophile, then the 2 electrons that were in this pi bond, they break and then they localize on this carbon here. So you would have a full carbanion here. But right next to it is you have a nitrogen with one of the oxygens having, with the nitrogen actually having a positive charge. So because this nitrogen has a positive charge, right away you have attraction from opposite charges. So this stabilizes that negative carbanion with the positive nitrogen. So this is why you must have your electron withdrawing group either ortho or para to your leaving group, so then you have that stabilization of that carbanion intermediate. And similar in B, you would have a strong nucleophile attacking the carbon that has your leaving group, being one of the halides, fluorine. You move around the pi bonds to finally make this bond here. When you make a bond, you have to kick off a bond, and your leaving group will fall off. And we know that this is the case because of that electron withdrawing carbonyl group that's right here.